Okay. So let's yeah, so this commutator subgroup, we're using it to kind of measure how abelian or not our group is. First, let's just explain how, in order to form this quotient, we need for G prime to be a normal subgroup. Okay, so let's do a little proposition. Let's say like phi is any homomorphism. Then phi of a commutator is just the commutator of phi, like a phi applied to its entries. And what that tells us as a corollary to this formula, we have that how to put this. I guess I want to if I take the conjugate of a commutator, that is just the commutator of the conjugates. Because we just apply this formula where when we replace phi with the map with the conjugation homomorphism. Okay, so this is a special case of this. And this means that, the conjugate of any commutator is another commutator. So it tells us that as a corollary, the commutator of G with itself, conjugate, is contained in like this, which is contained in commutator of G with G. In particular, so it just tells us that the commutator subgroup is a normal subgroup. Okay, and all that comes from this. So let's prove this line now. Oh, the commutator of G and H is just this thing. Now, being a homomorphism means that phi plays nicely with the multiplication in G. So if you want, we can do it step by step. This would be phi of G times phi of H, G inverse H inverse. Well, that's just phi of G, phi of H, phi of G inverse H inverse. And then also, so it turns out that phi of G inverse is just phi of G inverse. The same for H. And finally, this is just a definition of what the commutator of phi of G with phi of H. Okay. And let's just put a, so that proves the proposition, and the proposition tells us that the commutator subgroup is a normal subgroup. Okay, let me just remind you, why is 5G inverse equal to 5G inverse? So let's just do that as an aside. If we look at 5G times 5G inverse, that's just phi of G inverse. That's just phi of the identity, which is, if we want, we should put the identity of G, which is the identity of H. So a homomorphism takes the identity of one group to the identity of the other. And now if we, so this equation tells us that the inverse of phi of G is 5G inverse. In other words, 5G inverse. Okay, and that is a quick explanation of why we do one of those steps. Okay, so now we have that G prime is a normal subgroup of G. Okay, but not only that, we have this theorem. Let N be a subgroup of G. So if N is normal and G mod N is abelian, then G prime is a subgroup of N. Okay. That's the first part. 2, if G prime is a subgroup of N, then N is normal in G, and G mod N is abelian. So what this theorem says is that taking N to be G prime gives you the largest quotient of G, which is abelian. Let's just prove one of them. Let's prove this first one. And then that'll be it for today. So suppose N is normal in G, and G mod N is abelian. Okay. Let's define a homomorphism from G to G mod N, and the homomorphism takes an element G to the coset of G. And then, so phi is a homomorphism okay. Whenever you have a normal subgroup, you have this homomorphism. Okay, now we know that homomorphisms preserve a commutator. And so phi of a commutator is this commutator, which is in this group. But by hypothesis, G mod n is abelian, and in an abelian group, commutators are trivial. Okay, so therefore, commutator of phi of G with phi of H equals the identity. Well, this is the identity of G mod n. This is since G mod n is abelian. Okay. Therefore, this commutator is in the kernel of phi, the set of all things that get mapped to the identity. So we're almost done. Because the kernel of phi is the subgroup n. Remember that phi of G is just a coset of G, Gn. So if phi of G is the identity, the identity element, like the identity coset in G mod n is just the subgroup n. And then that applies that Gn equals n, which implies that G is in n. Okay. So this commutator is in n, and there's nothing like G and H were arbitrary, so all the commutators are in n. So the commutator subgroup is contained in n, and that was part one. Okay. So the commutator subgroup tells us like which, like how many, it tells us like whether or not G has certain abelian quotients, right? Okay, that is it for today. Thanks to everyone, to you all for coming out. Okay, bye.